Now looking at the principal quantum numbers that give the address of the electron in an atom. A discovery was made by Wolfgang Pauli called the Pauli exclusion principle, which states that no two electrons bound to the same atom can have the same set of quantum numbers. They have to be unique. Now this applies to all spin 1/2 particles, or spin half integer particles, spin 3/2, spin 5/2, and so on. So photons, which are spin 0, the spin momentum number 0, these bosons actually can pile on top of one another. They don't care if someone is already present. An example would be, imagine a classroom and you walk in and you see all the chairs lined up in all the different rows on the desks. Those are energy states, individual addresses that students can access, and assuming the class is full, the students would fall to the front of the class, start populating those chairs first, and then populating the middle of the class and then the rear of the class. Photons would just all pile onto the same chair. Electrons can't, right? Students can't sit on top of one another. Students are more like electrons, so they have to occupy their own personal seat in the classroom. So Pauli discovered this, and this is incredibly helpful when building atoms. So when we talk about atoms that have multiple electrons in them, those electrons have to have specific locations in the atom, specific energy levels that can't overlap with other electrons. So in an atom, electrons with the same principal quantum number, n, are called the same shell. So you have the n equals 1 shell, the n equals 2 shell, the n equals 3 shell for different energy levels in an atom. Electrons that have the same n and the same angular momentum quantum number, L, are in the same subshell. Now often, this angular momentum quantum number, L, is represented by a letter instead of a number, because you're already using numbers for n. So if the angular momentum quantum number L is 0, it's usually called the S subshell. 1 is the P subshell, 2 is the D subshell, 3 is the F subshell, and so on. So let's start putting electrons in an atom. Let's say we have an atom, a large atom like uranium, that has a lot of electrons. I'm not going to do all 92 of them, but let's start piling in electrons and seeing what possible energy levels and what possible addresses that these electrons can have, noting that the shells with low n number, n equals 1, n equals 2, will fill up first. Those are closest to the nucleus, and the outer shells will fill up at a later time. So let's get started. So the lowest energy state we can have is n equals 1. When n equals 1, that only leaves one possible value for L, right? L goes from 0 to n minus 1. Well, n minus 1 is 0, so L goes from 0 to 0, which is 0. M sub L goes from plus to minus L. Well, goes from plus to minus 0, so M sub L is 0. M sub S has to be either plus 1/2 or minus 1/2. So we'll start with a minus 1/2 spin down electron. And then the next electron that you drop in, n equals 1, still has to be L 0, M sub L still has to be 0, but I can put the spin at plus 1/2. Right? That's a unique address. They differ. And that's it. This is a shell. I cannot find any other relationship with n equals 1 that will be unique because of the constraints I'm under. So I have to go to the next energy level, n equals 2. Well, when n equals 2, L can be 0 or 1, right? L goes from 0 to n minus 1, n minus 1, n is 2, 2 minus 1 is 1, so L can go from 0 or 1. I'll start with 0. You can see that if L is 0, M sub L is 0, and then I'm going to do the minus 1/2, and I can do the same thing, same coordinates now, we have plus 1/2. I'm done with L equals 0. But L can be 1. If L is 1, M sub L can go from minus L to L, or in this case, minus 1 to 1 integer steps. So M sub L can be minus 1. Spin can be minus 1/2. You can have 2, 1, minus 1, plus 1/2. Now I'm going to carry it over here. I can do 2, 1, minus 1, I'm done. But I can go to 0, minus 1/2, 2, 1, 0, plus 1/2. And then finally, 2, 1, 1 minus 1/2, 2, 1, 1 plus 1/2. And that's all I have, right, for the n equals 2. I can't do any more. I used, for every L and M sub L value, there are 2 electrons that can fit in, a spin up and a spin down. So I'm trapped. This constitutes a shell. This whole n equals 2 is a whole shell, but remember that if it has the same n and L number, it's a subshell. This is a subshell. This shell is also a subshell. It's both. It has the both same n and L value. Here, n equals 2, L equals 0 is a subshell. We call that the S subshell for both, because L is equal to 0. When L is equal to 1, these here are a subshell. Actually, I won't write that there because I'll go to the next letter. That's the P subshell. The S subshell only holds 2 electrons. You can change which the 1s shell holds 2 electrons, the 2s shell holds 2 electrons, and we'll see the 3s shell also holds 2 electrons. Because n could be 3 now. L could be 0, 1, or 2. I'll start with 0. If L is 0, M sub L is 0. We have spin down, 3, 0, 0, spin up, plus 1/2. So here is a subshell, and 3s subshell. So we have, continuing on, then we would do the same steps as we had before. All the L equals 1 possibilities will give us the P subshell, and then M sub L, L could be 2 when n equals 3, and I have 10 more possible electron positions. So each electron, you can see, has a unique address given the constraints we had earlier, where we have n can go from 1 to, as big as it wants. L has to go from 0 to n minus 1. M sub L goes from plus or minus L, minus L to plus L, and M sub S is either 1/2, minus 1/2, or plus 1/2. What you can do here, let's see how many electrons do we actually have. When you write this out, you can write out these electrons in a specific format. Rather than writing out all of this long list, you can compact how you handle these electrons. So how do you compact this? Well, you can write it in a notation. I'm going to write it up over here. I'll use the purple. Where you can write the n number, the L letter, and then the number of electrons in that subshell. So this configuration would be 1s2, because the n equals 1, L is 0, that corresponds to the S subshell, and there are 2 electrons in it. 2s2, n equals 2, L equals 0, so that's the S letter, 2 electrons in that. 2p, because L equals 1 here, and we have 1, 2, 3, 4, 5, 6 electrons, 2p6. and then finally 3s2, because n equals 3, L equals 0, so you have the s shell with 2 electrons. And that would continue. If I added more electrons, you'd eventually have 3p6, 3d10, 4s2, 4p6, and so on. So when you're writing these out, and your book gives some examples, usually they only show you the last open configurations for the last energy level, assuming that if you're starting to fill in electrons at the n equals 4, that you filled in everything before that already. So this deals with basically spectroscopic notation, electron configuration notation, for how to write out the electrons in the ground state of the atoms in the periodic table.